Hello again, this is Mr. Wakefield here, and we're looking at section 8.5, and this is the last section, at least for now anyway, in chapter 8. We're looking at complex fractions. Complex fractions combine a lot of the things we've learned in the early part of chapter 8, but let's talk about right now exactly what a complex fraction is and what we need to do in these problems. So first of all, a complex fraction is a fraction with one or more smaller fractions in the top and the bottom, the numerator and denominator. Let me show you what I mean by that. If you look down here in the problems, you can see that there's a big fraction bar here. In all of these problems, you have the big fraction bars there. And I call them the big fraction bar because you have these little fractions inside of this big problem here with the big fraction bar. So you've got the big fraction bar, and then you've got smaller fractions. Okay, but the reason why it's a big fraction bar is because they want to emphasize the fact that we have little fractions within this one big fraction. So each of these problems is one big fraction, thus the big fraction bar, and then you have little fractions inside of it. All right, so for example, in this first problem, you got one big fraction with four little fractions inside. Two on the top of the big fraction, in other words, above the big fraction bar in the top here, and then two more fractions down below. Over here you have one big fraction, but there's just two fractions inside of it, one on top and one on the bottom. There's a couple of other terms there that go with it as well, the minus c squared and the 1. Okay, C and D are very similar to problem, C and 1 here are very similar to problem A, where they have four little fractions within the one big fraction. So our goal here is to simplify. Now that word simplify, we've heard that before more than one time, and each time you see it, it means something different. So we need to make sure that we clarify exactly what that means in this case. All right, if they give you a complex fraction and they say simplify, what exactly do they want us to do? Okay, well, there's two different methods that I present up here at the top, but there's just one that I'm going to actually do. So please do this method. It's going to be the first method here. It's a two-step process. They're two big steps, but nevertheless. The first step says write both the numerator and denominator as a single fraction. There's a very good reason for that. It's going to allow us to be able to do the second step. All right, obviously you want to be able to do the second step after the first step, but that's what's going to make it possible, is to get the first step done before you go on to the second step. What do I mean, though, by writing it as a single fraction? Well, if you have two fractions that are either being added, okay, or in the case of down here with these two fractions on top being subtracted, whether they're being added or subtracted, the way you make it into a single fraction, as we saw in the last section, is to actually go through the process of adding them together. Because when you add two fractions together, what do you end up with, you guys? You end up with a single fraction as an answer, don't you? Okay. So if I add 1/2 and 3/4 together, I'm going to achieve that goal that they set out for us, which is to make it into a single fraction. Okay, so what is the least common denominator? Remember, we need the least common denominator in order to be able to add these fractions together. For 2 and 4, it's going to be 4, isn't it? Okay, you can see there if we make the list for 2 and 4, the list of multiples, 4 is the smallest one there. Okay, so 4 is the LCD. All right. As we mentioned last time, you need to multiply by the appropriate thing in order to make the LCD go into the denominator, or in other words, to make the old denominator into the LCD. Okay, so if I go 2 times 2, that's going to do it, isn't it? And if you multiply the top by the same thing, in fact, that's what you're supposed to do. You're supposed to multiply the top by the same thing. You get 2/4, don't you? Notice, and we saw this in the last section as well, if your current denominator already is equal to the LCD, then don't change anything. Just keep it as it is, all right, because it already has what you want in the denominator, the LCD. Now that the denominators are the same, and since this is an addition problem, we now need to add the numerators together. 2 plus 3 is 5, and then the denominators stay the same. So we did it. We made the numerator, let me just bring it over here. We made the numerator into a single fraction, 5/4. Okay. Now we need to do the same thing with the bottom of the big fraction here, the 2/3 and the 3/2. We need to make that into a single fraction. Okay. Same thing. What is the LCD of 2 and 3? Okay. Using the methods we've learned before, all right, with multiples and everything, we end up getting 6 as the LCD. All right. So you need to what? You need to do what? 3 times 2 is equal to 4. 4/6. 2 times 3 gives me what? It gives me 9/6, like that. Okay, so now that the denominators are the same, I can add the numerators together since there's an addition problem on this step. The denominator again stays the same when you add and subtract. All right, and we end up with 13/6, like that. So that is the first step, to take the part that's above the fraction bar, the big fraction bar, make it into a single fraction, and then do exactly the same thing underneath the big fraction bar, make that into a single fraction also. Now that I've done that, I go on into step B right here, the second step, and that says to divide the numerator by the denominator. Okay, in section 8.2, we learned that. We learned that when you divide a fraction by another fraction, you what? You have to keep the first fraction the same, but then as we learned in 8.2, we flip the second fraction, and then it becomes a multiplication problem simultaneously. Let me make it very clear though, you guys. You have to make both of these things into single fractions first before you do the flip. That's why you got to do this first step where you make it into single fractions first. You can't flip both of these, for example. All right. You can't do that flip thing when you divide unless you have a single fraction divided by a single fraction. Okay, so everything has to be done in the correct order here in order to be able to do that division step where you change it to multiplication and you flip the second fraction. Okay. Now that I've done that, now that it's a multiplication problem, again, as we also learned in 8.2, we now cancel whatever we can before we actually multiply the tops and the bottoms of the fractions together. Okay, since all of these are single terms, you can start canceling right now as we learn in 8.2. You don't have to do any factoring first when you just have single terms in all four places here. Okay, if I start canceling right away, I can cancel 6 and 4, can't I? If I if I divide both of those by 2, I get 2 and 3 there. Okay. Excuse me. Hold on. There we go. And so that's the only thing I can cancel, right? Because 5 doesn't cancel with 2. 5 doesn't cancel with 13. 3 doesn't cancel with 2 or 13 either. Okay. In other words, the only common factors for any of those combinations, pairs of numbers there, is 1, and that's not going to make it any lower. Remember, the purpose of canceling is to make these numbers smaller, okay, by dividing by the same thing. So we're done canceling. All right. Now we have what? We now have 5 over 2. You don't have to write down the step if you don't want to. Okay, but I'm just going to clean things up like I normally do. And now that I've cleaned things up, let's go ahead and multiply these together. We get 15 on top and 26 on the bottom. And again, if we canceled everything that we possibly could, as we learned in 8.2, this should already be in lowest terms, but you're welcome to double check it. I can assure you that it is, though, if you don't realize it already. 15 over 26. Okay, so you should end up with one fraction as your answer in these problems that is in lowest terms. If you follow the steps, though, that should already, once you get down to the step where you multiply the fractions together, it should already be in lowest terms, though. Okay? Problem B. Once again, we want to put the part that's above the big fraction bar and the part that's below it, and we want to rewrite it as a single fraction. Okay. Now, how do you take a fraction being added or subtracted with just a term? See how here we have a fraction being subtracted with just a regular term? Down here we have a regular term being added with a fraction. The way you do that is you write the fraction and the term, but the term you put it over 1. In other words, you make them both into fractions. Okay, that way you can then do the normal thing where you find the LCD and all that. Okay. Now, whenever you have two denominators and one of the denominators is equal to 1, the other denominator is automatically your LCD. Okay. Because in reality, there's really only one denominator there, right? We just put the 1 in there as a second denominator just so that we can subtract these fractions. But in reality, there's really only C is really the only real denominator, right? And so, just like we said before, if you've only got one denominator, there's not anything to compare it to, and so that denominator's got to be the LCD also. Okay, so the C is the LCD. As we said in the last problem, if your current denominator is the same as the LCD, don't change anything. Just keep it 4 over C. But what do we need to multiply 1 by to equal C? Well, since 1 is just 1, you got to multiply 1 times C to get C, right? Because as you know, when you multiply by 1, it's the same thing. So 1 times C is C. So we multiply the top by that same thing, C. And again, remember, like we said in the last section, don't put the minus into the multiplication here. Okay, that's part of the subtraction step. So just do C squared times C, not negative C squared, but just C squared. And we get C to the third, don't we? Now we're ready to subtract. And like I said in the last section, if you're subtracting but you only have one term in the numerator that you're subtracting, you don't need to do that sign changing stuff. Just say 4 minus C cubed just as it looks. Just as it looks, okay? Like this. All right. And remember, those aren't like terms, so don't try to combine them. Okay, just say 4 minus C cubed. All right. Now we need to combine the 1 and the 8 over C. Once again, make the regular term 1 into a fraction by putting it over 1. And once again here, if you have two denominators but one of them is equal to 1, automatically the other one, as I just mentioned, is equal to that same thing, C. Is equal to in other words, it's always equal to the other denominator if one of the denominators is equal to 1. Assuming that you only have two denominators, okay, like we do here. If one of them's 1, the other one is your LCD. Okay, that means that 8 over C stays the same since the denominator already is equal to the LCD. But this one, just like in the last part there, 1 times C is C. And so we got to multiply the top by the same thing we multiplied the bottom by. And we get C over C. Okay, now, one of the biggest mistakes that I see students make is that they try to combine these. C plus 8. Remember, when you're adding or subtracting terms, you're not allowed to combine them. That's why I didn't try to combine this into one term here. Don't say 4C cubed. Don't say negative 4C cubed. Okay, you got to have a plus or minus in between it still, because it's that plus or minus that keeps the terms separate. And again, you're not allowed to combine them into one term if they're not like terms. So they should still have a plus or minus in between. All right. So as we talked about in Chapter 6 at the beginning of the semester, if you have two terms that you're adding or subtracting, if they're not like terms, then you should still have a plus or minus in between them to show that you didn't combine them. Okay, that they are still separate. So C plus 8 is C plus 8. You didn't combine it into one term. Okay? Like that. And so what happens now is, and I'll write it down on this step, is we have the top of the big fraction is equal to this. Like that. The bottom of the big fraction is equal to this right here. Okay. And so just like in the last problem, if you have a fraction on both the top and the bottom now, that means you're done with the first step. You made the top and the bottom of the big fraction bar into just a single fraction. So the next step is to flip the bottom fraction, because that's part of the division process. Flip the bottom fraction, keep the first fraction the same, like that. Okay, and then it simultaneously becomes a multiplication problem. Okay, now when it becomes a multiplication problem, if you have more than one term in any one of these four places here, you got to go through that whole factoring thing where you identify your factors after you're done factoring with the red and the green if you prefer. Okay, again, the colors are optional. All right, just want to make it easier for you here. And so when you have single term numerator and denominator, those are just single green factors, single term factors. Since both of these are prime, okay, this is prime because it has a GCF of 1 and it has c to the first power with two terms. This one has a GCF of 1, and no, it does not have c to the first power this time, but if you try to factor this, it doesn't work because, as we mentioned, when we have two terms, if you're on that step where you're trying to use one of those three formulas that we had back in 7.4, you know, the one where it's like a squared minus b squared or a cubed minus b cubed, those formulas. Okay, none of those work here because this one is a perfect square number because it's equal to 2 squared, but this one's a perfect cube because it's equal to c to the third power. All right, so in order to use those formulas, you either got to have everything in the two terms here, everything has to be either on the perfect square list or the perfect cube list, okay, in order to be able to use one of those formulas. So since the 4 is on the perfect square list and the c cubed is on the perfect cube list, all right, we can't factor it. So just a little review there of that. Anyway, so since those two things are prime there, I put a single red underline underneath them like usual. And now I'm ready to cancel if possible. Let's start out with the green things. The greens can be canceled here because they're exactly the same. They become 1 and 1. Okay, not that they always have to be exactly the same when they're green, but they are, so they become 1 over 1. We just divide both of these by, or pardon me, let me pull this off to the side. It's just like that when we said earlier, when you have variables, you take the smallest exponent, okay, and you subtract that from each one of these. Okay, so if you subtract 1 from both of these, you get c to the 0 power over c to the 0 power, which is 1 over 1. But to make it even simpler than that, I'm probably making it too complicated there based on this current situation. If you're trying to cancel variables, you guys, it doesn't matter what the exponents are. If they are the same exponent, it doesn't matter if it's 1 over 1 or if it's 3 over 3, okay, it automatically becomes just 1 over 1, okay, when the exponents are the same, assuming that the letter is the same as well, C and C. Okay, just so a little bit of review of that as well. So I'm done with the green ones. The red ones don't cancel because they're not, they don't qualify for canceling right there. Remember, in order to be able to cancel red ones, it either has to be exactly the same on the top and bottom, the two red ones on the top and bottom, or it has to have that opposite sign thing going on. These two things are not even close to either one of those possibilities. So we end up with this after I clean up my mess here. Okay. And if I now multiply those together, we get, anytime you multiply by 1, it's equal to itself. So we get 4 minus c cubed on top and c plus 8 on the bottom. Final answer. Okay. All right. So you can see those two steps now. Let's try one more problem here. Once again, the first step is to take the top of the fraction bar, make it into a single fraction. Take the bottom of the fraction bar, do the same thing. Let me start out with the top. Okay. As we learned in the LCD section, and by the way, there's no when both of the coefficients are equal to 1, you can skip the coefficient step when you do the LCD for single terms, like we did in the first couple problems back in 8.3. Okay. When we figured out the LCD for single terms, all right, we did the coefficient part first. That's where the 30 came from here. But you don't need to do that when the coefficient is equal to 1, 1a and 1b. There's an invisible 1 in front of each one of these variables, right? If the coefficients are equal to anything other than 1, that's different. But if they're both equal to 1, you can skip right to the variable step. And as we mentioned in 8.3, when you have a variable in one of the terms but not the other. See how the c is in this term but not the other? Okay, since we're taking the largest exponent, if you have no c at all and c to the third, it's going to be c to the third. Well, it's the same thing here. Okay, if you have no a at all down here but you have a to the first up here, then a to the first is going to go in the LCD. If you have no b at all in this term, but you have b to the first in this term, the largest exponent of b is b to the first. So the LCD is a to the first, b to the first, like that. Okay? Largest exponent of each different variable. Okay, when you have single terms only as your denominators and you're doing the LCD. What do we got to multiply by? Well, in order to go from a to a times b, wouldn't it make sense to just multiply by b? Because a times b is just that. It's a times b. Okay, you already had a there, so we multiply by b. So we multiply the top by the same thing, and we get 7b. Okay, since a times b is the same thing as b times a, because when you multiply two things together, it doesn't matter what order you do it in, it's still the same thing. Since a times b is the same thing as b times a, it would make sense that I would say b times a over here in order to get it equal to that LCD. And so we do 7 times a on the top, and we get 7a. Since this is a subtraction problem, I am now ready to subtract since the denominators are the same now. Since the since the numerators are not like terms here, though, do not try to combine them into one term. They should still have either a plus or minus in between the terms. And since you're subtracting 7a, you should have a minus in front of the 7a. They're not a plus. Okay? But you got to have that minus in between to indicate that you didn't combine the like terms. Okay. So that is the top part of the big fraction. The bottom part is similar. We're going to do 1 over a squared minus 1 over b squared, like that. And it is subtraction. What is the LCD here? The LCD is a squared, because you have a squared and no a at all, and that means the biggest exponent for a is a squared. For b squared, or pardon me, for b, for the variable b, you have no b at all, but then you have b squared. So the largest exponent between no b at all and b squared is going to be b squared. Okay? Again, you're taking the largest exponent of each different variable. And since the coefficients are equal to 1 on both of those denominators, you don't need to do the coefficient step. So a squared, b squared is your LCD. Okay. What do we need to multiply by? Well, again, since we have a squared times b squared, and since you already have a squared in the current denominator, that means it would make sense to multiply by b squared. That means we multiply the top by the same thing, b squared. 1 times b squared is b squared. that. Down here, a squared b squared is the same thing as b squared times a squared. Like I said in the last part there, it doesn't matter what order you multiply in. Okay, it's still the same thing as long as the two things are being multiplied. B squared is being multiplied by a squared. And so if I say b squared times a squared, it's the same thing as the LCD. Okay. And so the top, we have 1 times a squared is, anytime you multiply by 1, it's just itself. And so that's going to be a squared on the top. Now that the denominators are the same, I subtract the numerators. They are not like terms, so make sure that they are separated by that minus sign right there. Again, it's minus because we're subtracting the a squared, so we got a minus in front of the a squared, not a plus. Okay, and there you go. So we did it. We made, let me put it down on the next line so I have more room here, excuse me. I took the top of the big fraction bar and I made it look like this, right here. And I took the bottom of the big fraction bar and I made it look like this right here. Okay. And as we've been talking about in the last two problems, after you get a single fraction both above the big fraction bar and below the big fraction bar, you then, in the next step, keep the top fraction the same, but then you flip the bottom fraction and turn it into a multiplication problem simultaneously. Like that. Okay. Then, now that it's a multiplication problem and we have more than one term in a couple of the places here, that means we got to go through that whole factoring process. Okay. You don't need to factor the a, b, and the a squared, b squared because they are single terms. Okay. But these other two things you do, this is an LCD, or pardon me, this is a GCF right here when we factor. There's a 7 in there. Factor that out, we get this right here. Okay. And then down here, I can factor that because when you got b squared minus a squared, when you have something squared minus something squared, you can do that formula we learned in the end of the factoring chapter. Okay, it ends up being b minus a, b plus a. Okay. That's that first formula we saw in section 7.4. Okay, let's identify our factors here. For the first numerator, when you have a term times a bracket, that's our green and a red. When you got a bracket times a bracket, that is a red and a red. Excuse me, I got a little sloppy there. And then when it's just a single term numerator or denominator, it's a single green one. Let's start canceling now. Remember, you start out with the greens, and we have 3 green ones. So what you got to do is you got to pick one green on top. We have 2 greens on top here. Pick one of them to combine with one of them on the bottom and try to cancel it. 7 and AB don't cancel at all, but these two do cancel. How do they cancel? Okay. When you have a squared and a to the first, the smaller exponent is a to the first. Again, it's just like doing this right here, you guys. Okay, we picked out those 2 green ones right there, and it's just like doing this separately. If we had done this separately, we would subtract 1 from both of these exponents here, and that would give me a to the first over a to the 0, which is 1. And then you do the same thing for b. You got exponent 2 and exponent 1. You subtract 1 from both of those exponents, and you get b to the first. 2 minus 1 gives you b to the first. And 1 minus 1 gives you b to the 0, which is 1. And that's exactly how this turns out down here. This ends up being a over 1 and b over 1. like that. And now we have canceled all the green parts that we possibly can, because we tried to do the 7 in the AB, that didn't work. We did these two, and now if you look at what's left over, all I have left is 7. 1 times 1 is 1. That's not going to cancel, and then AB is not going to cancel with the 1s down here either. Okay, so the greens are done. Okay. Then we try to cancel the red ones. Okay. And what will cancel here? These two are exactly the same. And so that becomes 1 and 1 here. 1 over 1 when they're exactly the same and they're both red. And that's it, because we only have one red one left, so that's certainly not going to cancel with anything. Let's clean up our mess here. In the first fraction, we have 7 times 1 on top. Underneath that, I have 1 times 1 is 1. The second fraction, I have A times B on top. And then I have B plus A on the bottom. No bracket needed there because it's being multiplied by positive 1, as we said. No brackets needed. When you multiply a bracket times 1, it's just equal to the inside of the bracket now. Final answer here, when I multiply these together, 7 times AB is 7AB. And 1 times B plus A. Again, when you're multiplying a denominator times 1, you don't need to put the bracket around that. If the 1 was anything else other than 1, you'd have to take this times, and then you put a bracket around that next to it. But not when it's multiplied by positive 1. And there you go. So that is the two-step process for simplifying a complex fraction. Okay. Number 1 is very similar to problem C here. And then as you can see on the next page here, number 2 is also quite similar as well, a little bit different, but not too much. And then number 3, actually, the first step is already done for you. You see that here? Okay, you have this big fraction bar here, or bigger anyway than the other fraction bars. This big fraction bar, it's got a single fraction on the top and bottom. So that means that step 1 has already been done for you. It's completed. And so you can jump right to that step where you flip the bottom fraction and then you just do the rest of the steps like you normally would. Okay, so please try 1 through 3. We'll take a look at those answers in just a moment when you hit the play button. And then we'll wrap things up here in section 8.5. Number 1. Again, we need to take the top of the fraction bar and the bottom of the fraction bar and make it into a single fraction. Let's start out with the top. 1 over a squared minus 1 over b squared. I needed to multiply, pardon me, I'm going a little bit too fast there. The LCD is a squared b squared for the same reason as it was in the last problem. Okay, a squared is the largest exponent of a, b squared is the largest exponent of b. We multiply by the appropriate things here. Multiply this one by b squared, multiply this one by a squared. And that gives me these two results that you see here. Now that the denominators are the same, I can subtract the numerators, but don't combine them since they're not like terms. Make sure that minus is still in between there. And so now the top is done. Now we need to do the bottom here. Okay, subtract those so that it'll become a single fraction. Let's see how that looks. The LCD for those two fractions, notice that they don't have to be the same LCD as these ones because, again, you're doing a whole separate subtraction step here. Okay, we subtracted these two, but then we're subtracting these two separately. So the denominators don't need to be the same LCD, and they're not. This time it's AB. A to the first and b to the first, those are the largest exponents of a and b. We then multiply by the appropriate things here, b on this one, a on this one. We then get b and a as my two denominators. We now are ready to subtract them. Again, when we subtract, they're not like terms, so keep the two numerators separated by the minus there. Okay, since it's minus a, we're going to say minus in front of the a there. And now we did it. We made the top and the bottom into a single fraction here. So now we're on to that step where we need to flip the second fraction and make it into a multiplication problem simultaneously. We then what? We then need to factor this, okay, and try to factor this as well. These two things don't need to be factored because they're single terms, okay. B minus A, by the way, is prime for the same reasons as before. GCF of 1. You have two terms and your variables are to the first power, automatically prime. This, however, becomes what? This becomes B minus A. Let me read it to you here. I know it's kind of hard to read. B minus A, B plus A. B minus A, B plus A. Okay, I already did my canceling there. And then the B minus A, actually, let me not go too fast, excuse me. Let's do the greens first here. The AB cancels with the A squared, B squared, just the same way that it did in the last problem. Okay, for the same reason. They're both green. You cancel the A's and you cancel the B's. The difference is that this time the variables are on the bottom, okay, because the A squared, B squared was down there. And the AB is now on top, okay. And then here you cancel the B and the A, the B minus A with the B minus A, since they're exactly the same. It's going to be 1 and 1. Okay. Let's clean up our mess here. Cleaning up my mess here, I get B plus A is all that's left on the top of the first fraction. AB is all that's left on the bottom of that fraction. And then 1 and 1 on the other two here. You can see nothing but 1s here. Multiplying that back together, what's my final answer? B plus A over AB. Okay? And that is number 1 right there. Okay, so lots of stuff going on here. 2 steps, but 2 big steps, right? Okay, let's move on in here to problem number 2. In number 2, again, same idea. We need to take the top here and make it into... let me go ahead and zoom in here so we can see it better. Okay. We need to take the top of the big fraction bar and make it into a single fraction. The LCD is 4a squared. Why is that? Why is the LCD 4a squared? It's because when their coefficients are not equal to 1. See how the coefficient here is 4, but the coefficient, I'm looking at just the denominators. Coefficient here is 4. The coefficient here is 1 in front of the a squared. So as I mentioned in 8.3, when we did LCD, if you have 2 denominators, one of them has a coefficient of 1. The other coefficient, if it's not equal to 1, that will automatically be your LCD. Okay, for at least for the coefficient part. So 4 goes into the LCD. Don't look at this here. This is the next step. Looking over here. The 4 goes into the LCD. And then the reason why I put a squared with the 4 is because that's the largest exponent. Okay, we have no a at all here. And then we have a to the second. Okay, and so the largest exponent for a is a to the second. So putting that all together, 4 and a to the second are your LCD. Okay, so we need to what? We need to multiply by the appropriate things here. 4 times a squared gives me the LCD, so I multiply the top by a squared as well. Down here, I already have a squared in the denominator, so I need to multiply by 4 to get 4a squared, because again, a squared times 4 is the same thing as 4 times a squared. So times 4 would be the appropriate thing to do there. Now, 1 times 4 gives me 4 right here. As always, you guys, now that we're ready to subtract, since the numerators are not like terms, keep that minus sign in between there to indicate that you didn't combine them. And now that's the numerator of the big fraction. The denominator is similar, as you'd expect. The LCD is 2 times a. Okay, for 2 and 1, you get the LCD is 2. Okay, and then for no a at all here and a to the first, you get a to the first. That's the largest exponent of a. Okay, so we multiply by the appropriate things here. 2 times a is 2a. A times 2 is 2a. So I know I did the right multiplications there. Multiply the top by the same things, and we get a and 2 as our numerators. A and 2. We now add those numerators together. A plus 2 is a plus 2, because they're not like terms. So we got to keep that plus, not minus this time, but plus in between those two terms, because we're adding the 2. So the plus and not the minus has to go in front of the 2 right there on top. So now we've got our two fractions here. Single fraction on top of the big fraction, single fraction on the bottom of it. We now do that step where we flip the second fraction. First fraction stays the same. The only thing that needs to be factored here is the a squared minus 4, because the a plus 2 is already prime, and then these two are just single terms. A squared minus 4 is a squared minus 2 squared, and so we get this right here. Now let's cancel. 2a and 4a squared. If I cancel that, since they're both green, it's just like pulling these off to the side and canceling these, and we know how to do that now. 2 and 4. If I divide both of those by 2, we get 1 and 2. Again, we've done these not only since then, but we've also did them back at 6.4, where you got the single term on top and bottom. Okay. 2 and 4 becomes 1 and 2. The smallest exponent here for a is to the a to the first, so we have 1 minus 1 is a to the 0, and 2 minus 1 gives me a to the first. And so we end up with 1 times 1 and 2 times a. 1 times 1, 2 times a. Let me write those down right there. There they go. All right, and then amongst the red ones, these two cancel, don't they? Because they're both exactly the same. Let me clean up my mess now. I'm done canceling completely. And it looks like that right there. And whenever you multiply by 1, it's just equal to itself. So the final answer is right there. Okay, so that is problem number 2. Problem number 3, as I promised, is one in which the first step is already done for you. Okay. And so the first thing I did right there was to move over the, pardon me, not move it over, but to flip the second fraction here. When you got a single fraction on top and a single fraction on the bottom, you flip the one on the bottom. Since we have more than one term in some of our 4 places right here, a couple of them right here, we need to do the whole factoring process. Okay, so I did that here with a minus 1, a plus 1. The a plus 1s cancel. Nothing else cancels there. Going through the normal canceling process. And we just end up with this right here. Cleaning up my mess, this is what we end up with. And then multiplying those fractions together. I officially get a minus 1 over 1, right? But as you know, when you have 1 as a denominator, you don't have to write it in your final answer. We did write it earlier in the in some of these problems because of the fact that when you're trying to add or subtract it with another fraction, you got to make something into a fraction there as well. All right, we saw that back here where I had to make the c squared into a fraction. Okay, so that's a situation where you do need the 1. But usually if the final answer has a 1 on the bottom, you don't have to write it. Again, it's not wrong to write it. If you want to put the 1 underneath the a minus 1 with a fraction bar, you're welcome to do that. But you don't have to. So you could write this, okay, but it's just easier to write this, right? Okay, so that concludes complex fractions, section 8.5. We'll revisit chapter 8 later on in the semester, but right now we're done with chapter 8, and so we'll start chapter 9 with the very next video. In the meantime, though, let me know if you have any questions about not only this section, but also chapter 8 with fractions and everything. Okay, you have a good day, and take care.